Sir, please unmute your mic.
Okay, so let us start the class. Before we begin, I'll address if you have any questions. Can you hear me now?
Yes, sir, we can hear you.
And so I have to take the mid-sem exam. So when you will paper mid-sem exam? So by next, today is Thursday. So next Thursday will be fine. So next Thursday, 10 o'clock, I'll take the exam. I can start little bit early also, but you may have class. And if you have problem with this date, please find any other suitable date before next Thursday. You can have all student has to agree. So that is why I prefer to take the exam during the class, because nobody can have any objection for taking the classes exam during the class. Okay. So this will be final, that we'll have exam on Thursday 10 o'clock, maybe 9:45 I'll start exam, but I'll finish the exam sharp at 11, because you may have some class at 11, and I want to stop the exam at 11. So syllabus for the exam will be still the mechanical similarity, which I taught in the last class before Dashera. So that will be your syllabus. Today onwards, whatever will teach will not be there in the exam. And also I'll ask Dr. Krishna whether he wants to take a separate exam, or he wants to give question in my exam. If he agrees, then we'll have only one combined exam. If he wants to take separate exam, then he will announce, he will schedule his exam. Okay, but you people know, since you are in 5th semester, that your sessional marks will be on the exam, assignments, your performance. This will matter. Okay, and then we'll finalize your sessional marks depending on all these parameters. But main parameter is your exam, and I'll try to take an exam in a manner that to minimize that copying each other. So let me see how I can find that. I want to make it in such a way that student will not able to copy much on that. Any queries, question on exam, or any question regarding last lectures? If you want, we can have a tutorial class also. I'll give you a old problem set which I used to circulate. Today I'll circulate. If I forget, please remind me in WhatsApp. And then we can have a tutorial class before your exam, but that will be not in the scheduled time, scheduled lectures, because I missed a lecture on last Saturday. Not last Saturday, when I missed a lecture, yeah, last Saturday, 9th October, I missed a lecture, and we can compensate on that by taking a tutorial class some other time, not in the. So you find in the evening session, afternoon session, mostly I am free. Even 9 o'clock session also possible. Some days I have classes for Monday, Tuesday. I don't have class on 9 o'clock, but it is still possible. Or in the
Sir,
evening.
sir, can you please take next Wednesday, because I will be traveling on Thursday. I'll be in train.
Wednesday you don't have a class, so that is the problem. And I have a class for MSc students, and I'll taking exam on next Wednesday. So, but Wednesday afternoon is possible. But in that case, all student has to given me in writing that they are agreed to that schedule. If you can arrange, I can take.
No, sir, I think there's a practical on that day. Okay,
Hmm.
I will
Yeah.
discuss it.
Yeah, you discuss and we can. So let me know tentatively your exam in Thursday, uh, and it is not that hard and fast. I have to stick to that time. I can. I'll be flexible to reschedule it a little bit, but we want to complete in that week. So.
Yes, sir, you may take any day in that week. I don't have any problem. But on that day, I'll be in train, so that's why I was asking.
Okay. Yeah, but suppose I schedule it to Saturday class, then and somebody else is also traveling on that day, then there will be trouble. So Saturday, and only 36 students are 34 students are present, and so let us, you think about the student and let me know in the group by today evening, then I'll announce. Uh, there is two possibility, either Wednesday, Thursday, this hours, or maybe in the Saturday class. Saturday I have a class, so that class also I can take exam, but not beyond that. Saturday this week, next week I want to finish the exam, because Saturday itself will be very close to Deepavali, and people may say that we'll be leaving on Saturday, because Saturday, then Sunday, then Deepavali will come, so people may leave. So if student pay for Saturday, then I can take. Otherwise, this that is why I fixed this Thursday. But anyhow, so let us start the class. You people decide, you discuss among yourself in your group, and then tell me. So today, what we'll discuss is the virial theorem. Last day I discussed mechanical similarity, which is also a very powerful method. Today I'll discuss virial theorem. You can see that is another powerful technique in classical mechanics. Let me first state it, and then I'll prove, and then we'll find how it is useful. So these are the steps. So first I'll state the statement. So suppose you have a particle has a finite motion. A particle, suppose a particle is subjected to a force uh, Fi. Say, there are many particles. So say ith particle has force I. Suppose so ith particle. I'm just having explaining statement, etc. You take it from good book. So I suppose I have a system of particle. I have system of particle, and this is my system. And I'm considering the ith particle is subject to the force Fi, and its position vector and position vector is Ri, and the motion is taking place. All these statements are important in a finite region of space. This is very important. Finite region means particle will never go to infinity. So there is no possibility that particle will go to infinity or can escape from the closed region. So particle in a finite region. That means R cannot go to infinity. Okay. So this position vector never can become infinite. So this is, then the average kinetic energy of the system, this average, this long time average, this also long time average of the kinetic energy particle t, and this bar means long time average, is given by minus half sum over I f I, this force on the ith particle, dot uh, r I. These are vectors and whole thing is average. So average means long average, long time average. So average kinetic energy can be given by this force dot product between the force on the particle into its position vector and sum over all particles, sum over all such particles. So this is suppose n particles, so I going to 1 to n, and then this is also average. Okay. So average kinetic energy, now we know average kinetic energy, then also very easily we can find average potential energy, because average total energy is the total energy. Average total energy is the total energy. So very easily we can find. So this is the statement of Eulers theorem, and let us prove it. Okay. So proof is very simple. So only thing that we should assume, which we already assume, that kinetic energy is a homogeneous function of velocity of degree 2. This is a very reasonable assumption, that is half mv square u. This is that better now, Shruti? I'm okay. This if the kinetic energy is a homogeneous function of the velocity of degree 2, this we know. Kinetic energy is right half mv square, so it is degree 2. If you have more than two particles, one particles, then you can have v1 square, v2 square. You can have also v1 dot v2. This is also similar to v1 dot v2, is also a uh, quadratic function of velocity of degree 2, homogeneous function. But you cannot have v1 cube, or you cannot have v1, v2, v3, three velocity, because this kind of things are not there in the kinetic energy. But this is a very reasonable and good assumption. Okay. Okay, so if that is true, then I can immediately write that v ith particle dot del t del vi sum over vi is 2t, right? Because degree 2. So this is Euler's theorem. So because of Euler's theorem, I can write. Also, I can use the equation of motion, equation of motion, Newton's law, Pi for each particle. So rate of change of momenta is the force, right? Fi. This also we can write. Okay. So now let us see can get also one more thing which I should tell you, that you remember your momentum is for ith particle will be del L del Vi, right? This we know. This is the definition of the momentum from the Lagrangian. So this is basically same as del T del Vi. Of course, again a very reasonable assumption, assuming that potential energy is not velocity dependent. Velocity dependent potential we have not discussed so far. We'll discuss velocity dependent potential. So differentiating Lagrangian is t minus u. So del L del V will be del T del V minus del u del v, but we are assuming that u, potential energy, is independent of velocity, so this is 0. Okay, so this is pi, so I'll substitute del L del Vi by pi. So let us come back to this equation. So this equation again, so will be Vi dot pi, del T del Vi is pi, sum over all particle should be the total of the kinetic energy. This equation further I'll rewrite in a simple way. This is Vi means Ri dot, and this is Pi. So this I can write ddt of sum over I Ri dot Pi minus sum over I. This ddt is okay in the whole term, and then it is Ri dot Pi dot, right? Because this derivative of product of two terms will be, the first term will be derivative of R dot dotted with Pi, R dot dotted with Pi. Second term will be R dot dotted with Pi dot. So I am taking a total derivative, so I am subtracting this. So that will be this. Okay, I think this is simple. Okay, so my 2t, then my 2t is ddt of sum over I. Simple mathematics, you should able to follow, minus sum over I Ri dot Fi. No, Ri not dot, this is vector. Pi dot is Fi, that Pi dot is Fi. This is the Newton's second law. So that I substitute here. Ganesh Kumar, hello. Hello, Ganesh Kumar, can you speak? Ganesh Kumar, unmute and can you speak? Why you are coming in this 20 minutes late, 18 minutes late? Can you explain? Ganesh Kumar, otherwise you leave this class. If you cannot unmute, then I think, and cannot speak, please leave this class.
सर पता नहीं था।
क्या पता नहीं था?
सर क्लास
टाइम टेबल आपको मालूम है? आप जब बीएससी क्लास कर रहे हैं, एक टाइम टेबल होता है
सर। तो
टाइम
आज
टेबल, हाँ
सर आज
बताओ।
बृहस्पतिवार है तो बृहस्पतिवार को नहीं था ना आपका क्लास?
हाँ तो क्या हमने
तो
ये शुरू से, आज ये 10th क्लास 11th क्लास हो रहा है, आपको पता नहीं है? तो आप अभी जाइए, आराम करिए थोड़ा सा, इसमें अभी पूजा का टाइम है ना, तो थोड़ा आराम करिए, जाओ क्लास से जाओ, निकलो, लीव दिस क्लास। अगर जब करना है तो टाइम में आ जाना। Okay, so this is the now I'm going to take a time average of this. So average, concept of average is clear to everybody. If not, you can do this simple problem. Suppose you go to Allahabad from Varanasi with a vehicle 30 kilometers per hour and return by 40 kilometers per hour. So what will be its average speed? You go 30 kilometers per hour, return back 40 kilometers per hour. What will be your average speed? It is not 30 plus 40 divided by 2. That you have to understand, because distance is fixed. So when you go by 30 kilometers per hour, you take more time than when you return back by 40 kilometers per hour, right? If it is 120 kilometers, so you will take 4 hours to go, but you will take 3 hours to return. So weighted average you have to do. So average speed will be 3 hours, 4 hours you will run with 30 kilometers plus 40 kilometers you will run 3 hours divided by 7. 4 plus 3, 7. So this will be your average speed. So basically it is a the time interval, that how much time you are traveling with how much speed, and divided by total time. So this is average when you have a time period of a function, say tau is time period, and then you want to take a average of some quantity, say xt, this in this time period. So its average time average is you should integrate this function dt and divided by the total time. This is the total time, and this is the product of this function time dt. And then here I have two, but when I do a continuous variable, so I have to integrate this summation. Here we have a summation, summation is replaced by integration. So time average over of a function xt over a time tau is 1 over tau 0 to tau f xt dt. So this is called the time average. Okay, I think everybody is familiar with that. Now I'm going to take a time average of this equation. So this is my equation. I'm going to take a time average. So left hand side I'll not do anything, but I'll put a t bar. Okay, right hand side, this equation is total derivative, so I can integrate. So this is d tau integration over d dt of sum over I r I vector dot pi. This is sum over I and this whole thing, and then minus sum over I ri dot fi. Here I cannot do anything, so let us put the bar again. In this term only I put in this formula because I can perform the integration, because it is total derivative. This term is total derivative, so I can perform the integration. Total derivative and time integration, so I can do. But this term and this term I put a bar because I cannot make any simplification. So this term will be 1 over tau. This integrating will give you this term, and integration is 0 to tau. So sum over I ri dot pi dot, and this quantity at tau minus the same quantity at 0 will be the result of this integration. This ddt and this t will go away, so we can integrate this, and then this has to be calculated at tau minus this quantity, same quantity has to be calculated at 0, and of course minus sum over I bar ri dot fi. Okay. Okay, so this is the formula. So this is minus, and this everybody understand that what I'm explaining. Now long time average, come to that point. Long time average. That means I am not taking average for a brief time. I am taking for very long time. So mathematically long time average means tau going to infinity. Mathematically. Long time average. Long time average means, so now look at this quantity at the limit tau going to infinity 1 over tau. Then you have in the numerator sum over I ri dot pi at tau minus sum over I ri dot pi at 0. Right? Now let us point to another important thing that I said, that finite region of space. Finite region of space. That means particle can never go to infinity. So r is finite at time t. R is also finite at t at initial time t equal to 0. So this difference of two finite quantity is finite. Okay, difference of two finite quantity must be finite, and it is so this is a numerator is finite, denominator is 1 over tau, so this limit will be 0. Okay, so ri dot pi at tau and ri dot ti at 0 is a finite quantity independent of tau, constant quantity. This is a constant quantity, this is also a constant quantity, their difference is finite because particle can never go to infinity. So this is a finite independent of tau quantity divided by 1 over tau. Now if I take a limit tau going to infinity, this will be 0. So now go back to my formula. 2t bar is minus half, this term will be remaining, I ri dot fi. Okay, so t bar will be minus half sum over I ri dot fi. This average will be, of course, will be. So this is the proof of virial theorem. Okay, any question on this proof of virial theorem? I think this is straightforward. Okay, now let us go to the go to some application. Okay, so in application, let me consider that suppose your force can be obtainable from a potential, so minus del u del ri, say. So you can write that your t bar is minus half sum over I ri dot del u del ri average. Okay, I just no, this will be plus because f is minus, so minus minus plus. Now let us assume that u the potential energy is also a homogeneous function of coordinates of degree k, suppose k in general. So this again Euler's theorem I can write. So this you can write that this term will be k of u. So this will be k by 2 u bar. Right? R dot del u del r is nothing but k times u, because I am assuming that u is also homogeneous function of coordinates of degree k. K can be minus 1, plus 1, 2, 3 or kind of thing. Right? So k will see for different potential, and then for this situation, this kind of potential conservative system and u is homogeneous function of degree k, you find t bar is k by 2 u bar. Right? Also total energy is nothing but your t bar plus u bar. Okay, so now if I substitute my t bar is k by 2 times u bar plus u bar as a total energy, so this will be k plus 2 by 2 times u bar equal to E, total energy. So in this situation u bar will be 2 by k plus 2 times total energy, and t bar will be k by k plus 2 times u, because t bar plus u bar will be E again, right? So this we find a very interesting formula for average kinetic energy and potential energy for a system which is potential energy is a homogeneous function of the coordinates of degree k. Now let us consider whether this example or this result is correct or not by considering few problems, few examples. So examples. So suppose for harmonic oscillator, simple harmonic oscillator, U is half m omega square x square, right? This is the potential energy for a harmonic oscillator. So k equal to, for this potential, k equal to
2.
k equal to 2. So k equal to 2. So I can get my U bar k equal to 2. So it is half total energy. T bar is also half total energy. So U bar equal to T bar. That you know. For a harmonic oscillator, average kinetic energy is same as average potential energy. This you must have studied. Okay. Now k equal to 2. Now let us say you have a free fall particle falling freely from a height. So U equal to mgz. So again k equal to 1. In this case k equal to 1. So U bar will be 2/3 of total energy and T bar will be 1/3 of the total energy. That means U bar equal to 2T. For a freely falling body, this is the result. Similarly, if you have, say, Kepler's problem, Kepler's problem, that potential energy is alpha by r type of, right? That means k equal to -1. If k equal to -1, then let us calculate average kinetic energy. Average kinetic energy will be -1 plus 2, so minus E. Is that wrong result? Because average kinetic energy is negative of the total energy. Is that wrong?
No, sir. Bounded system.
Good. So it is a bounded system. E is itself negative. So this is not that average kinetic energy is negative. Of course, average kinetic energy cannot be negative quantity, right? But this is not a negative quantity. E is itself is negative. So E less than 0 bound problem. So this is not a contradiction. Now and U bar of course will be 2E because their addition has to give you 2E. That also you can find from k equal to -1. So denominator will be 1, numerator will be 2. So 2E. Okay. So this. Do you have any question? Otherwise, we'll move to. You must have one question. If you don't have, then you are not fully understanding this. That is why I asked. I generally should explain that, but
Sir, if k is equal to -2.
yes, so that is the question you must have in your mind. So if you have a potential U as minus a beta by r square, then k equal to -2, and then there will be difficulties. K equal to -2, then denominator is 0. So this formula will not be valid. This formula will not give you a sensible result. The U bar will be infinity, T bar will be infinity. So where is the problem? Problem is that when you learn central force problem, you will find if you have this kind of potential, then motion is not restricted to finite region of space. You can see that particle can go to infinity if you have this potential. So when you learn central force problem, I don't know whether I'll teach or Dr. Krishna will teach, you'll learn that if you have 1 over r square potential, particle can go to infinity. And if particle can go to infinity, then our virial theorem cannot be valid, because at the beginning, at the statement I wrote that motion has to be in the finite region of space. Finite region of space. Okay. Okay, so this is all about virial theorem, except one remark. So in exam, sometimes we ask that if you have a potential, say x, y, z, like half x to the power 4 plus a 3 by 7 x cube z plus 9 by 11 x square y square, as a complicated potential, and you don't know this system, you are not familiar with this system. So and then if we ask that what will be the average potential energy and kinetic energy under the virial theorem, then you can immediately know this system if is unknown system. But if I know that this motion is within the finite region of space, then you can immediately think of that this will be system will be described by k equal to 4, because this is power 4, this is 3, this is 1 4, this is 2. So you have to check the whether it is a homogeneous function or not. If it is not homogeneous function, then you can directly, you cannot use that. But if it is a homogeneous function and then k equal to 4, so your uh, q bar and t bar you can calculate. So it will be 4 by 4 plus 2 times e. So it is 4 by 6, so it will be 2/3 of e, and this will be 1/3 of okay. Okay, so this kind of question we sometimes ask in the exam, that giving a complicated potential and asks you to find that what will be the kinetic energy and potential energy. This is all about now if you have understood this class, you have known almost everything about the virial theorem, which I am supposed to teach in the classical mechanics. Okay, so now we'll move to another topic. Now, velocity dependent potential we have not discussed, and now it is time to go to that direction. And for that, we need to go back to our very beginning discussion when we discussed the constant system of constants. I mentioned in the class that there are two difficulties in the two difficulties by when the constraints are present. One is that all coordinates are not independent, right? All coordinates are not independent because there are constants. Constant will relate coordinates. But if you have a holonomic system means constant equation you can write as a equation, and you can eliminate those. So you can find the number of independent variables, and those will be generalized coordinate. And then you can go through Hamilton's principle and describe the motion. But if the system has a non-holonomic constant, or the system or this function is so complicated that you cannot eliminate all these coordinates properly, then there may be some. This is of course algebraic problem, not a conceptual problem. Then will be another problem. So another problem is due to that all we don't know all force of constants are not known, or the nature of, let me write, nature of all the forces of constants are not known a priori, before starting the problem. When you write the free body diagram of the problem, That time it is not known what will be the nature of constants. So in this situation cannot be handled, then you cannot go to the Hamilton's principle, and you need another approach to find equation of motion, because constant of force, constant of what is constant of force? Force that causes the constraint, that is not known a priori beforehand. So then we need another approach to find equation of motion, and I mentioned that that is called D'Alembert's approach. And this, with using the D'Alembert approach or D'Alembert principle, I'll explain what is D'Alembert principle. You can also find the equation of motion. D'Alembert's principle considers something called virtual displacement. This is a this is little bit of tricky concept because of virtual. This word virtual means which is not real. This is not real. You have to imagine such situation to handle this second situation when the force of constants are not known. So we have to think in such a way that effect of the force of constant is somehow we can compensate with something. Okay, so we don't know the nature of the force of constant, so effect of that, if we can compensate with something, then we can deal with such system. And to do this, we need a concept which is called virtual displacement. So virtual displacement, and let me write real displacement. And you know the work done is related to virtual displacement, right? Work done W equal to this, how you write, it is F dot dr kind of. So if this dr is the virtual displacement, I'll explain what is virtual displacement. So then this work will be virtual work done. Virtual means you are imagining. What you have to imagine, that I'll give you in the definition. And when you have a real displacement, then you have the real work done. Real is which is we can calculate, which is we can feel, but virtual you have to imagine only. Okay, so let me define and then we'll explain. And we'll define with a thing that it is uh, uh, it is with infinite decimal. So let me define that infinite decimal infinitesimal virtual displacement. Virtual displacement, let me write Vd. So change in the configuration of the system, let me write the change in the configuration of a system uh, as a result of any arbitrary infinitesimal change infinitesimal change of the coordinates this is delta Ri coordinates consistent with the force forces and constraint imposed. So this change of coordinates, which is consistent, I'll explain this, consistent with the forces and the constraints impose in the system on the system at a given instant of time, at a given instant of time. This is very important, at a given instant of time. Okay, let me explain. So this is this statement which I wrote here is a definition of infinitesimal virtual displacement. So it is the displacement you write as a delta Ri. So it is the displacement delta Ri of the but which is consistent with the forces on the system. You have a system, that means there are forces. What are the forces? Forces is the external forces, there are mutual forces, there are forces of constraint. So it should be consistent with all forces and the consistent and the constraint imposed on the system. Constraint imposed on the system means it is also consistent with the forces of constraint. But most important thing is that, or different with the real displacement, is that given instant of time. That means particular instant of time, delta t, there is no time interval for virtual displacement. No time interval, it is in a particular time. Because if you have a interval in real in contrast to the real displacement, real infinitesimal displacement, uh, in this case you have, there is a delta t which is not equal to 0, there is a time interval. But problem is that if there is a time interval, then in that interval the forces will evolve, the system will evolve according to forces. Force also evolve. See, if it is a time dependent force or if it is a force which changes, so that forces at the beginning of the interval, at the end of the interval, they changes. So you have to deal with differently. So real displacement, you have delta, you have interval where this displacement is happening. But when we define virtual, that is why it is virtual. It is difficult to imagine that it is the displacement at an instant of time, no interval. So that is the difference between real displacement and virtual displacement. Okay. We'll come a little bit more. You think about it, try to realize with some examples of virtual displacement. But I want to cover in 10 minutes. We want to cover certain things. Okay. So now suppose the system is in equilibrium. Now the system is at equilibrium. It's not moving. It is now you have reached to a static. You can think of a static. So after you have motion, and so you can think of that force acting on individual particles Fi is 0 for a static situation, and no movement, no dynamics is happening. So in that case, virtual work done will be 0 because force itself is 0. So Fi dot di will be 0 because all Fi are 0 for I equal to 1, 2, 3, or all particles. If it is a continuous, then also it is, but all forces are 0 for static situation when in the equilibrium situation. But to obtain equation of motion, we have to come out of equilibrium, that will consider. But total force, this total force can be the applied force plus the forces of constraint. Ith particle, and let me write the force of constraint. Okay. So I can write this integration as Fi a applied force plus force of constant, but this total force is 0, right? So dotted with let me write delta r, this virtual displacement is equal to 0. So in the static situation, virtual work done is 0. Now that F, but notice now F A is not equal to 0. Applied force is not equal to 0. You have only the total force. In the equilibrium situation, the static situation, you have the total force equal to 0, not the applied force equal to 0. Now the D'Alembert's approach comes in the play. Up to that, this is only the concept of virtual displacement. Now D'Alembert principle says that we can think of the system in such a way, or we'll consider the system for which, so we consider the system or the type of virtual displacement such that the this virtual work done by the force of constraint equal to 0. So now we consider, let me write this statement, we consider the systems for which the virtual work done by the forces of constraints are 0. That means Fic dot delta I is 0. We are taking such, we are considering this to deal with the forces of constant. So we are considering the virtual work done by the constant of force is equal to 0. So this equation then will reduce to Fa applied force dot delta Ri equal to 0. So this statement is sometimes called is the D'Alembert's principle, but it has many different forms. So D'Alembert's principle is that it is a principle. Principle is that the work done, virtual work done by the forces of constant is 0. This is the principle, and that principle will give you the equation of motion. But this is a principle again, like Hamilton's principle. We don't know how it comes. That is the brilliant mind that they understand that this will give you the correct equation. Principle of least action or Hamilton's principle. We don't know. There is no proof that how this principle comes. There is no proof for the D'Alembert's principle. D'Alembert's principle is that the work done by the virtual work done by the forces of constant of a system is 0. This has many different form of this equation. So this equal to 0. So if this equal to 0, so I substitute this equal to 0. So this part is remaining. So this is the virtual work done. But statement and this mathematics are little bit of different. And this may realize this virtual displacement. See, if you have suppose you have a spherical container and particle is sitting on the top side. Now the force of reaction is that particle is constant to move on that surface, is that force of constant is perpendicular to the surface. Now the particle try to move, it will be tangential, but force of constant is vertical, so work done will be 0 because its displacement and the force, if they're perpendicular to each other, then so this is an example of realizing that how virtual work done by force of constant is 0. Okay, so this is the thing. And now you understand, I already mentioned Fa are not equal to 0. For example, F1 dr1 plus F2 dr2 plus F3 dr3, for example, is 0. but all f1, f2, f3 are not 0. This implies that r1, r2, r3 are not independent, right? So that automatically the D'Alembert's principle put the condition that all the coordinates you are considering, they are not independent. But that is the thing we want. We earlier we did it by eliminating. I have the constant equation, I eliminate those, and I found that who are the independent coordinates, and we name those are the generalized coordinate and do Hamilton's principle, got equation of motion. Now here D'Alembert's principle, by putting this, that by this is the principle, and virtual work done by the forces of constant at 0, that gives automatically that coordinates are dependent to each other. That is the only thing we want to do. Now how much time? 4 minutes. So now I'll consider that, okay, now we are coming apart from the equilibrium, so away from equilibrium, away from the equilibrium. So in that case, fi, the fi, the applied force here only, the applied force will be the pi dot, right? Generally this is the Newton's law. Okay, just a moment. Okay, no, what I am saying, that if you have the away from the equilibrium, so if you have a away from the equilibrium, then you have mm, just let me put the correct wordings for this. When we have away from the equilibrium, then how we write the D'Alembert's principle, that is the important thing. Okay, so when we are away from the equilibrium, then let me, this is little bit of misleading, this let me erase. Okay, so when we are away from the equilibrium, then there is a balance force. If there is a net force in the system, then we have only we are away from the equilibrium. You are in the equilibrium means there is no force, and in that situation you can write your fa is as pi dot. But if it is if you are away from the equilibrium, there is a net force, then fia minus pi, that will be the effective force, right? This is the force due to Newton's law. This is the force we are taking here. So if you are away from the equilibrium, system will have some residual force. If there is no resultant force in the system in the equilibrium, and that force is this force. So D'Alembert's principle, if you want to discuss away from the equilibrium, then will be, looks like fa, this all are applied. Now constant force is nowhere. This, that is why I minus sorry, pi dot delta ri should be equal to 0. That resultant force, this will be the force. Now henceforth we remove the subscript a. Now we did not, because repeatedly will not write, this is same as f. Okay, so now D'Alembert's principle is fi minus pi dot, all are vectors dotted with delta ri vector equal to 0. Now in next class, this in Saturday's class, we'll start from here, and now we'll assume that not all r are independent, but there are generalized like q1 to some qi, those are independent. So when we express this D'Alembert's principle in terms of generalized coordinate, then we'll get a equation of motion that will be the similar to the Hamilton's principle equation of motion. So in today's class, we explain the D'Alembert's principle. In next class, we'll consider this D'Alembert's principle in Saturday's class, and we'll find the equation of motion. And then we'll realize that this equation of motion is bit general compared to the equation of motion we obtained through Hamilton's principle, and we'll see that velocity dependent potential also we can discuss. Some type of velocity dependent potential, not all types, can be discussed, and then we'll study the velocity dependent potential. So next few classes will be on the velocity. First we will derive this equation of motion due to D'Alembert's principle, and then from there velocity dependent potential will discuss, and then certainly the charged particle in the magnetic field will appear. So this will do. Okay, so I'll stop here. In next class I'll do this. Read this D'Alembert's principle or the Veriel theorem. If you have queries, question, bring it to the class next time. Also, I'll circulate the problem set. If I forget, please remind me in the evening, by evening. And then what will happen that we can have a, if you have time, then we can have a tutorial class. Okay, any question? And attendance is very poor. I don't know this. I believe that there are 50 students, but initially there was only 36 37 students. So this is ridiculous. And the mid-sem exam, after exam you will feel that what is the effect of not attending the class. Okay, I stop recording the class.